All right. So we really just have one more task to accomplish in this section on the optimal growth model. And that is to prove what I believe is proposition 3 in your lecture slides. Which says the following: in the neoclassical optimal growth model, where all of our assumptions hold, including the one regarding the utility function, the economy is going to monotonically converge to the unique steady state capital to labor ratio, K star, starting from any arbitrary value of capital, okay? So if initial capital is less than the steady state, then that means KT will converge up, increase monotonically until the steady state is met. If K0 happens to be bigger than the steady state, then KT will converge monotonically down, and the sequence will be strictly decreasing until the steady state is hit. What does that sound like to you? It sounds like to me the transition dynamics that look like the solo growth model, right? It doesn't matter what the initial stock of capital is, we're going to have this kind of monotonic convergence to the steady state. The neoclassical optimal growth model exhibits the exact same behavior. So even though we're solving an infinite horizon utility maximization problem, and even though firms are behaving optimally, and all of those features of the model are endogenous compared to the solo model, where things like savings behavior was exogenous, you still get the same type of long-run behavior in the economy, where the capital stock will monotonically converge to its steady state value, okay? And basically what I want to do today is do a proof of this proposition, and then I guess it's another proposition after this that talks about the monotonic convergence of the path of consumption. But that's going to follow quite easily and directly from this proposition 3. This is the main one we'll talk about today, and then we'll be done with this model. Okay. So how do we want to prove this? Remember that KT plus 1 is going to be a function, an optimal time invariant policy function of the state KT for all t. So the solution to our dynamic programming problem gives us a policy function S that shows how KT maps optimally into KT plus 1. We also know that the policy function S is non-decreasing for all KT in the space that is feasible for KT to exist in, 0 to that upper bound K hat that we characterized in the last class or the class before, I don't recall. This, by the way, I think this was proposition 1, right? Remember I told you that we would use this result, that the policy function is non-decreasing in the state, in order to prove the stability properties of this model later on, okay? So S is a non-decreasing function. This implies then that if, let's say K1 is our optimal value of capital in period 1, given the initial state of capital at time 0, K0, that means K1 is either going to be bigger than initial capital, or the optimal value of capital, again equal to S of K0, will be less than K0, right? There's only 2 possibilities here. Either K1, that is our optimal choice of capital in period 1, is either going to be bigger than or equal to initial capital, or it's going to be less than initial capital, okay? I want to consider the behavior or the time path of the capital stock in each of these 2 cases. and try to demonstrate that regardless of which case we're talking about here, the capital stock is going to converge monotonically to the same steady state value in the long run. All right, let's consider case 1. So here we have our optimal value of first period capital, K1, we're assuming is bigger than what our initial given value of capital is. This is the case we're considering. Okay? Well, if K1 is bigger than or equal to K0, then we know that S of K1 has to be bigger than or equal to S of K0, right? Because S prime of K is greater than or equal to 0. Again, that's proposition 1. So if we assume that K1 is bigger than K0, then that means S of K1 has to be bigger than S of K0. Well, what's S of K1 equal to? That's going to tell us what our optimal value of K2 is, right? And what is S of K0 equal to? Well, that tells us what our optimal value of K1 is. So what we have shown here then is that if K1 is bigger than K0, it follows then that K2 has to be bigger than or equal to K1. You guys follow that? Okay. Now, if K2 is bigger than or equal to K1, then we know that S of K2 has to be bigger than or equal to S of K1. And again, that is because S prime of K is greater than or equal to 0 by proposition 1. But if S of K2 is bigger than S of K1, then that means that our optimal value of K3, which is just equal to S of K2, has to be bigger than or equal to our optimal value of K2, which is just equal to S of K1. So K3 is bigger than or equal to K2. We can do this for an arbitrary number of periods, but what we're going to find by induction, we can show that KT, which is equal to S of KT minus 1, will be bigger than or equal to S of KT minus 2, which is equal to KT minus 1, for all t bigger than or equal to 2 in this case. So KT is bigger than or equal to KT minus 1 for all t bigger than or equal to 2. Okay, now you will recall that the capital stock is always going to be an element of a compact set defined by 0 to k hat, where you guys remember what k hat is. It's the k hat is the max of initial capital or this highest sustainable level of capital, k bar, where k bar is characterized by f of k bar is equal to delta k bar. We got that in the last class. So KT always has to reside somewhere on this compact subset of the reals. So what have we shown here? The sequence KT from t is equal to 0 to infinity is a non-decreasing sequence in a compact set with initial capital bigger than 0. we've got so we've established that for this first case, the capital stock is a non-decreasing sequence, right? And we also know that the capital stock has to live on this compact set of the reals, all right? Now, this means, think about this, you've got a non-decreasing sequence that exists on a compact set. So what must happen eventually to the capital stock? This implies that the sequence KT converges to some, I'm going to just call it K infinity, all right? That's greater than 0 because initial capital is bigger than 0 and the capital stock is rising, or at least it's not decreasing over time. So because it resides on a compact set, that means that it necessarily has to converge to some fixed point. Let's call it K infinity, where K infinity will satisfy, obviously, this equation. K infinity is equal to S of K infinity. You can think of this fixed point as being the supremum of this sequence of points for the capital stock defined on this compact set. Now, we know that K star, the steady state value of capital, is unique. We proved that in Prop 2, I believe. It follows then that this fixed point that the capital stock has to converge to is indeed going to be equal to the unique steady state value of capital. Right? So the limit then, as t goes to infinity of kt is equal to K star. And since the sequence of capital stocks is non-decreasing, that means that kt is going to converge up towards the steady state monotonically, and initial capital is of course less than the steady state. By the way, maybe you guys didn't quite understand this, but you've got a sequence of capital stocks over time. That sequence we proved is non-decreasing. It's effectively rising over time. But the capital stock has to live on this closed and bounded set. It can never exceed K hat, right? So that means that if we take time on out to infinity, the sequence has to converge to some point, right? Isn't that, somebody with better math background than me, isn't that the monotone convergence theorem from, where do you learn that? In analysis or advanced calculus? I don't remember. It's been...
Or you could say that it's bounded above by...
Yeah, I think that's the monotone convergence theorem. Nathaniel, you're the math major, isn't that right?
Sounds good.
It sounds good, right? But it makes sense, right? The sequence is increasing, but it's got to be, but the capital stock is bounded from above, and so eventually it has to converge to some point. I think that's the monotone convergence theorem. If you've got a sequence defined on a compact set that is strictly increasing, then it has to converge to some point, right? And because the only fixed point in this sequence is the steady state, which we proved in Proposition 2, then it must converge to the steady state. I think that's the monotone convergence theorem. Okay, let me show you a spectacular degree of laziness here. Let's do case 2, where we're assuming this time that K1 is actually less than K0, right? I'm going to use as little bit of graphite as possible and use my eraser more now. Okay, so this is case 2. K1 is less than K0. Well, that's going to mean that S of K1 has to be less than or equal to S of K0 because S is a strictly or is a non-decreasing function, right? K1 less than K0, then that means S of K1 is less than or equal to S of K0. That was prop 1. Well, if S of K1 is less than or equal to S of K0, then that means K2 is less than or equal to K1, right? And if K2 is less than or equal to K1, then S of K2 is less than or equal to S of K1, again, because the policy function is non-decreasing. And if S of K2 is less than S of K1, then that means K3 is less than or equal to K2. See how I'm being lazy here? You don't get to be lazy, I guess. You've got to show both cases, but I'm going to do a shortcut. If we repeat this over and over again, you're going to find that KT, which is S of KT minus 1, is going to have to be strictly less than or equal to S of KT minus 2, which is the same as KT minus 1 for all t bigger than or equal to 2. So KT is less than or equal to KT minus 1 for all t. In other words, what we've shown here is that if K1 happens to be less than the initial capital stock, then the entire sequence of capital stocks is going to be non-increasing. It's going to be decreasing over time, right? It's exactly the opposite of the situation described in the first part of the proposition. Okay, now, again, the capital stock has to lie on this compact subset of the reals, 0 to k hat. And KT is a non-increasing sequence defined on this space 0 to k hat, where initial capital has to be, of course, something bigger than 0. So KT is a non-increasing sequence on this compact set. All right, by the monotone convergence theorem then, the sequence KT is going to converge to some limit point, call it K infinity. I'm not going to necessarily say it's bigger than 0 though, where K infinity is the fixed point of our mapping S, which shows how KT maps optimally into KT plus 1. Again, that is the monotone convergence theorem. If we've got a closed and bounded set and a sequence is strictly decreasing on that set, then it has to converge to some limit point. Let's call it K infinity, okay? Now, K star is the unique steady state in this model with positive activity, right? However, there is actually, in this case, I've got to make a small adjustment. There are 2 candidate values for K infinity. This limit point along this non-increasing sequence could be K star, but what is the other possibility that it can converge to? Well, it can converge to the lower bound on our compact set between 0 and k hat, right? We knew in the first part that K infinity would not be equal to k hat because K star is less than k hat, right? And we assumed that initial capital was less than K star. Okay, so there's 2 possible candidate values here, right? 0 and K star. All right. We want to rule out this one, obviously, okay? And how do we do that? Well, I'm going to take a shortcut, and that shortcut is based on a small assumption that we made early on in our discussion of this model. I told you it would be useful later on, but not to harmful, okay? You guys might recall that the utility function, the domain of the utility function was between some epsilon and infinity, and that the utility function mapped that space onto the reals, right? Where epsilon was some small number greater than 0, okay? In other words, consumption can't be below this infinitesimally small positive number, right? So consumption has to be bigger than or equal to epsilon for all t. Well, let's think about what happens to consumption if indeed k infinity is 0. Consumption at infinity would be defined by f of k at infinity plus 1 minus delta times k at infinity minus k at infinity. Well, what's that going to be equal to? That's f of 0 plus 0 minus 0 is equal to 0. Remember, capital is an essential input. F of 0 is going to equal 0. And that would violate this assumption that the capital stock has to be strictly bigger than or equal to epsilon. So we can rule out this no activity convergence point by appealing to the fact that consumption cannot be equal to 0 in this model, okay? So the limit as t goes to infinity of kt has to be equal to k star when k0 is bigger than k star. And so you get the capital stock declining monotonically to the steady state. So parts 1 and 2 of this proof are basically the same, except in part 2, we have to just appeal to that assumption 6 to rule out the possibility that k infinity is equal to 0. All right, so regardless of the initial stock of capital, whether it's higher than the steady state or lower than the steady state, we see in the optimal growth model that the capital stock is going to converge monotonically to that fixed point in the long run. Behavior that is observationally equivalent to what we see in the solo growth model. And this is one reason why the solo model is still used as a good working example, is because even though the assumptions are totally unrealistic, that agents always save a constant fraction of their output, that there are no markets, right? There's no utility maximization. It's just strictly kind of an exogenous growth model. It generates behavior in the long run that looks very similar to what you see in a model that endogenizes a lot of those features. Okay, you guys have any questions then about that one? No? Does it make sense? Okay. Let's go on then to proposition 4, which in a lot of ways follows directly from proposition 3. So what prop 4 says is that really there's two parts here. The optimal policy function for consumption, not the capital stock, so I'm going to call that C of K, is non-decreasing. And if capital is less than the steady state initially, then the sequence of consumption is going to be such that consumption converges up towards the steady state. But if capital is bigger than the steady state initially, then the sequence of consumption is going to converge monotonically down towards the steady state. So basically two parts to this proposition. The optimal policy function for consumption, defined as C of K, is non-decreasing. So if the capital stock gets higher in period T, that will immediately lead to higher optimal levels of consumption in period T. Furthermore, not only do we have monotonic convergence of the capital stock to the steady state, we have monotonic convergence of consumption to the steady state. So in that sense, the optimal growth model is globally asymptotically stable for all of its key variables. All right, any questions about what it says? Let's work through a proof. And really, the most important part of the proof is the first part. Because if we can establish that the optimal policy function C is non-decreasing, then the second part follows almost trivially from the first, right? Because as the capital stock is rising monotonically to the steady state, if the policy function for C is increasing, or at least non-decreasing, that means the consumption is also going to be increasing towards the steady state as the capital stock rises, because C and K have a positive relationship between one another. If the capital stock is falling towards the steady state, then consumption must also be falling, given the positive relationship between consumption and capital. So really, we just want to prove this part. That's the main piece. That's not too hard to do. How do I want to do that? Let's take two values of capital. Let's call them K and K tilde. And I'm going to assume that K is less than K tilde. All right. But both K and K tilde are going to be values of capital in the interior of the feasible domain. Right. This compact subset of the reals. If K is less than K star, then what do we know? S of K has to be less than or equal to S of K tilde. And that is by proposition 1. Yep. All right. What does the first order condition of the Bellman equation look like for both of these values of the state? For K, you should have the following: beta V prime S of K is equal to U prime of F of K plus 1 minus delta K minus S of K. That is by the Euler equation. Now let me stop there and make sure you guys understand that. So imagine we'd set up the Bellman equation for this optimal growth model and we just took the first order condition. What is that first order condition? It's negative U prime plus beta V prime is equal to 0, right? So beta V prime evaluated at optimal capital then must be equal to the marginal utility of consumption evaluated at the optimal policy, S of K. That's just the first order condition, or the Euler equation. Well, if instead the state was equal to K tilde, what would the Euler equation look like? It would be beta V prime S of K tilde is equal to U prime F of K tilde plus 1 minus delta K tilde minus S of K tilde. So both of those are by optimality, basically. Now, if S of K is less than or equal to S of K tilde, we immediately know something about the relationship between the derivatives of the value function evaluated at each of these two optimal policy functions. Which one is going to be bigger, V prime of S of K or V prime of S of K tilde, if S of K is less than S of K tilde by assumption and by proposition 1?
V of SK tilde would be larger than V of SK.
V prime of SK, be careful there, Richard, would have to be bigger than or equal to V prime
I agree.
by, and why is this? Why is V prime of S of K bigger than V prime of S of K tilde?
policy function is increasing S of k tilde. So when the gradient of S of k would be, the gradient of the value function with respect to S of k would be small.
Hold on. Be careful. It's not that V is increasing, it's that V is concave. That's theorem 4 in our dynamic programming. Concavity of V. Because the utility function is strictly concave, we proved that the value, and because the constraint set was convex, the value function itself is strictly concave, which enables Tavoy for us to have a unique policy function that solves the dynamic programming problem. So V is strictly concave. Therefore, if S of k is less than S of k tilde, that means the derivative of V at S of k has to be bigger than the derivative of V at S of k tilde. So V is strictly concave, just like the utility function is, just like the production function is. That's one of the beauties of working with concave functions, is you immediately know something about the relative sizes of the derivatives of the function evaluated at two different points, right? The slope of the value function falls as the point at which you're evaluating it increases. Now, why is that helpful? If V prime of S of k is bigger than V prime of S of k tilde, it follows then that we know something about the right-hand side, right? Then that means that U prime of F of k plus 1 minus delta k minus S of k has to be bigger than or equal to U prime F of k tilde plus 1 minus delta k tilde minus S of k tilde, right? If V prime of S of k is bigger than V prime S of k tilde, they're both multiplied by betas here, so that's no different. That means the right-hand side of the first one has to be bigger than or equal to the right-hand side of the second one. So U prime of C of k then has to be bigger than or equal to U prime of C of k tilde. And what does that imply then about C of k relative to C of k tilde? The utility function is strictly concave. So if U prime of C of k is bigger than U prime of C of k tilde, that means C of k has to be less than or equal to C of k tilde, QED. We started off by assuming that there was k less than k tilde. What we wanted to show was that C is non-decreasing. And we find from this argument that C of k is less than or equal to C of k tilde. So indeed, C is a non-decreasing function. All right, let's take the case again where K1 is bigger than K0 is bigger than 0. We already showed from proposition 3 that the sequence KT is non-decreasing. On this compact set 0 to k hat. That implies then that KT converges to this unique limit point, K infinity, which we know has to be equal to the steady state. And it converges up towards the steady state. Because consumption is a non-decreasing function of the capital stock, then this is going to imply that the sequence of consumption is non-decreasing. Again, that's because C prime of K is greater than or equal to 0. And so CT then will converge up to some C star, where C star is defined as the value of consumption once the capital stock has hit its steady state value, F of K star minus delta times K star. So if we start off with an initial value of capital that is less than the steady state, the sequence of capital stocks is going to be rising over time on a compact set and will therefore converge to the steady state value of capital. Because consumption is a non-decreasing function of the capital stock, consumption must also rise as the capital stock is rising. And once the capital stock reaches a steady state, consumption will reach its steady state equal to F of K minus delta K star. And of course, exactly the opposite happens if K1 is less than or equal to K0. We've already seen from proposition 3 in this case that the sequence of capital stocks is non-increasing on 0 to K hat. This implies that capital is going to converge down to the steady state, where we can rule out 0 as the limit point of this convergence, because consumption has to be strictly positive at all times. So the sequence of consumption values is non-increasing because, again, C prime of K is greater than or equal to 0. As capital declines over time, that means consumption has to decline over time as well, because the optimal policy function for consumption is non-decreasing. So CT will converge monotonically down towards the steady state anytime initial capital exceeds the steady state value of capital. So not only do we have monotonic convergence of the capital stock, we have stable monotonic convergence of consumption as well, which really follows from this point. I mean, it's almost trivial, right? If consumption is increasing in the capital stock, if the capital stock converges monotonically, so will consumption. Okay, you guys have any questions about that? To Void.
Yeah, so how would we contrast this with the golden rule of consumption? Is that, could we say that that stability point is where the golden rule of consumption occurs?
Not quite. We're going to, so that's going to be a major point in the next model that we discuss, the neoclassical growth model. It turns out in these infinite horizon settings, what we understand as the golden rule, that is the level of consumption in the steady state where the marginal product of capital is equal to delta plus N, I believe is the criteria. In the neoclassical growth model, that doesn't quite hold, that the steady state level of consumption is actually slightly less than our understanding of what the golden rule is. Now, there's a good reason why that is the case. And it's because of we'll get into this more in the next section, but it's basically because of the fact that you're discounting in these models. So if you imagine you're at a steady state that is below the golden rule, well, how do you increase consumption? You have to save more to increase the capital stock so that you can increase output and consumption in the long run. But because of the property of discounting, which we didn't account for in the solo model, these permanent increases in consumption don't always outweigh the losses in consumption you experience in the transition period, because future higher consumption is going to be discounted more than the losses of consumption you experience in the near term. So what happens in the neoclassical model is something called the modified golden rule, which adjusts our understanding of the golden rule to take into account discounting that affects the transition to the steady state. So you get something that's similar to the golden rule, but not exactly the same. And that will be more readily seen when we talk about the neoclassical growth model. Okay. Okay, so I promised that if I had time, and it looks like I do, we've got about 20 minutes left. I want to show you guys an alternative method for solving or setting up these dynamic programming problems where there is an analytical solution. So if you'll allow me for a few minutes to go back to the canonical model. So this is the one that has logarithmic utility, Cobb-Douglas production, and full depreciation, right? You guys remember, hopefully, that the Bellman equation in that case looks like the following. V of k is the max of k prime on g of the log of, what is it, k to the alpha minus k prime plus beta v k prime for all k on its feasible set, which is 0 to, this k hat, right? Where we've defined k hat slightly differently in the canonical model. I believe k hat was the max of k0 or 1. And g of k is equal to the interval defined by 0 to k to the alpha. All right, so that's the statement of the functional, the recursive statement of the optimization problem in the canonical growth model. Okay, now how did we solve this analytically a few class periods ago? We took the first order condition as well as the envelope condition, and we updated the envelope condition, scrolled it forward one period, substituted that back into the first order condition to give us this Euler equation. And what did we do at that point? We made a guess of the policy function, correct? And we used a undetermined coefficients or a guess and verify strategy to solve for the policy function directly. That's the way I like to approach these problems, but there is a different way. It involves guess and verify, but instead of guessing directly the policy function, you can guess the value function, all right? Let's assume that we know what that guess is, that the value function, you guys recall the correct guess was that it is constant e plus constant a times the log of k, right? That was the appropriate guess of the value function. The value function should take on a similar form as the utility function. Well, what if we worked with this value function directly by substituting this guess directly into the Bellman equation? If we do that, when we take first order conditions, we no longer have any value function arguments, and we can solve the first order condition directly, right? So now the Bellman equation becomes the max of k prime of the log of k to the alpha minus k prime plus beta times v of k prime. Well, that's just beta times e plus beta times a times the log of k prime. Maybe this way makes more sense or is easier for you to think about. Okay. we can take first order conditions of this maximization problem. That's just going to be -1 over k to the alpha minus k prime plus beta times a times 1 over k prime. All that's equal to 0, right? Can't we solve this equation directly for k prime? Yeah, so we've got, let's see, beta a over k prime is equal to 1 over k to the alpha minus k prime. So we have what? If I cross multiply, you've got a k prime is equal to beta a k to the alpha minus beta a k prime. So 1 plus beta a k prime is equal to beta a k to the alpha. All right, so k prime looks like it's a beta a over 1 plus beta a, all of that times k to the alpha. That looks like it's going to have the right functional form for the policy function. It's going to be some constant times k to the alpha, right? But the thing is, we don't know what this coefficient a is. So how do we determine what it is? How do we figure out what a is? Well, what you want to do is you want to substitute your solution for k prime back into the Bellman equation and match coefficients, right? So remember, the value function is e plus a log k. That's v of k, right? What should v of k be equal to? It's the maximized value of the right-hand side. So just go plug in your solution for k prime back into the right-hand side, and you get the log of k to the alpha minus k prime. So that's beta a over 1 plus beta a k to the alpha plus beta e plus beta a times the log of k prime, which is beta a over 1 plus beta a times k to the alpha. I don't have this one in my notes, so hopefully I'm doing it right, but we'll find out. I actually think doing it this way involves a little bit more algebra, but it might be more straightforward conceptually for you. We should be able to group terms here, right? This is k to the alpha minus beta a over 1 plus beta a k to the alpha. So that's a log of what? 1 plus beta a minus, that's a 1 over 1 plus beta a k to the alpha plus beta e plus beta a log of beta a over 1 plus beta a k to the alpha. Now the log of products can be separated, right? And so what are you going to get? You're going to get a constant, which I don't care to write, plus what? You're going to get an alpha log k plus beta a alpha log k, right? This constant here is going to be complicated. It's going to be equal to the log of 1 over 1 plus beta a plus beta e plus beta a times the log of beta a over 1 plus beta a. That's just in this, that's the constant which we're going to match to e. I'm not going to do that, but you can. All I care about is matching the coefficients on the log of k. And so what must be true? A, if we now match coefficients, has to be equal to beta, now this can't be right, yeah, beta a alpha plus alpha, right? So 1 minus alpha beta times A is equal to alpha, or A is equal to alpha over 1 minus alpha beta. Is that the right answer? Well, let's find out. Remember that K prime was equal to beta A over 1 plus beta A K to the alpha. And we just determined that A is equal to alpha over 1 minus alpha beta. So what is this intercept term? I'm sorry, this coefficient on K to the alpha in the policy function? That would be what? Alpha beta over 1 minus alpha beta divided by 1 plus alpha beta over 1 minus alpha beta times K to the alpha. So that's alpha beta over 1 minus alpha beta divided by, let's see, 1 minus alpha beta divided by 1 over 1 minus alpha beta. Oh, look at that. Cancel, cancel, alpha beta K to the alpha. That look familiar? So that method also generates the correct policy function for the capital stock. It should also generate the same solution for the value function. You just have to go through some more algebra to solve for E. So does everybody see conceptually the two methods there? You can set up the Bellman equation, derive the first order condition and the envelope condition, combine those two to give you a intertemporal Euler equation, and then you can do a guess and verify strategy directly on the policy function. That's method one. An alternative way is to set up the Bellman equation and do a direct guess on the value function, get the first order condition from that, solve for the policy function from that first order condition directly, plug it back into the Bellman equation, and then match coefficients in the Bellman equation. From those matched coefficients, you can then figure out what the policy function is. I prefer the first method. It's a bit more straightforward for me, but I remember in grad school learning this other method, and a lot of other of my colleagues preferred solving them this way. I don't care. To me, the policy function is more important economic quantity to obtain, because that tells us precisely how the capital stock and therefore consumption are going to evolve over time. What we care about is consumption and capital dynamics. And so solving for the policy function directly seems to be more straightforward. But either method is suitable. And that's all I have. So if there's no other questions, starting on, let's see, next Monday, we're going to begin about a 4 or 5 class session. It's going to take at least 2 weeks to go over the neoclassical growth model. The equilibrium that emerges in this model is going to be identical to the one we've derived here. So all of these cool results, like the existence and uniqueness of the steady state, the stability of the steady state, and exactly what that steady state is, particularly in the canonical model, also emerge in the neoclassical model, okay? However, in that model, there are some new concepts that are important to understand that don't emerge in the optimal growth model, mainly the household's budget constraint and the lifetime budget constraint, which is, we're going to spend an entire class period talking about that and how it relates to this transversality condition. The neoclassical growth model also gives rise to this concept of a saddle path equilibrium, okay, where you have not only states but co-states that you have to think about dynamically over time. And so we're going to illustrate the dynamics of that model using something called a phase diagram. So I think it's still a very useful model to work through, because even though it generates the same results in equilibrium, there are new concepts and quantities that come up in the discussion of that model. Once we get through that, you guys will have your next exam. You know, that's looking like early November, okay? And then we will move on to stochastic growth models. So we've got to spend some time talking about how we modify our dynamic programming theorems to account for randomness, for random variables like stochastic technology shocks, for example. And then we want to apply those theorems to the stochastic optimal growth model. What happens now if the production function gets hit with random technology shocks over time? It's that class of stochastic growth models that are the precursor for the so-called real business cycle and new Keynesian business cycle models that are studied today. All right, so we have to see how we introduce stochastic concepts into these particular types of models. So far, all we've talked about are these kind of perfect foresight deterministic models. And then once we finish that, the last topic will be looking at a different class of models and a different type of equilibrium altogether, a Nash equilibrium, as opposed to this kind of Walrasian, decentralized, competitive equilibrium, to study some phenomena that we see in labor markets, namely unemployment, okay? And that will be it for the semester, but that's going to take another month or so to get through that. See you next week.